Friends, our today's topic is second order low pass filter. Second order low pass filter. First order low pass filter was dealt in a previous class. So let us see how it is different from first order. Okay. This is your circuit and this is how the frequency response is. Okay. In your circuit, if you see this circuit diagram, second order is almost same as your first order. Second order is almost same as first order. The only difference is one resistor and another one capacitor is extra added in your circuit, right? If I remove this part, this is your first order low pass filter. If I remove this part, right, one resistor and capacitor, and there is a feedback resistance, this is your first order low pass filter. If I add this R and another C, R1 and C2, this becomes second order low pass filter. Second order low pass filter. Okay, and this capacitance C2 is once again taken and connected to output side. Fine, and this is how the response will be. Initially, the gain will remain equal to 1 for all the lower portion of the frequency. Okay, for all the lower portion of the frequency, your gain will remain 1. Gain will remain 1, because of which this part of your portion of the signal will be allowed. When your frequency further increases, when it increases, your gain starts falling down. Okay, your gain starts falling down with a rate of minus 40 dB per decade. Minus 40 because this is second order. In first order it was 20, right? Minus 20. Here it is minus 40 because another RC network is added. With one RC network you will get 20. With another RC network you will get 20 plus 20, that is 40 dB per decade. So it will become more steep. It will become more steep. Slope will increase here, right? More quickly it will fall down. More quickly the gain will fall down. Understood? And when your gain starts falling down at minus 3 dB, when it cuts, that cutting frequency is called as cutoff frequency. Okay. Now we'll see how to find out the value for C1, C2, R1, R2, R3. Okay. Yes, I am writing a very important point here. If you see this frequency response, let us analyze what when the frequency is at lower portion, and in the other case when the frequency is at higher frequency portion. Okay, let us analyze first in lower frequency. Okay, at low frequency, let me write this. At low frequency, XC1 and XC2, this capacitive reactance, okay, is much larger, isn't it? Because we know that Xc is equal to 1 over 2 pi Fc. When frequency is less, Xc is going to be very high, isn't it? So with this concept, I am writing this statement. Xc1 and Xc2 are much larger than R1 and R2, isn't it? Yesterday in our first order low pass filter class, I have shown you with the equations, right? With the output equation, what is the relation between Xc and R1 and R2? You can refer my previous class for this. Hence, I can write both Xc1 and Xc2 have no significant effect on the circuit, as if it is absent in the circuit. It works as if it is not present in the circuit. Okay. Therefore, the output voltage V0 is equal to the input and the gain of the is unity. Okay, I'll write 1, isn't it? This capacitance at low frequency is so large that the effect will be only such that it will give you unity output. Means the gain becomes 1. Gain becomes 1. Better I write 1 here. Gain is 1. How the gain becomes 1, we have analyzed in first order low pass filter. Okay, you can refer same topic for that. And till your gain is 1, till your gain is 1, you are in this portion. You are in this portion. Okay, so this part of the portion of this signal will be allowed to pass. It will not be blocked by the filter. Okay, till your gain is equal to 1. Understood? Now let us see what happens when it is at higher frequency. Right, at high frequency XC1, okay, I'll write in terms of capacitance. At high frequency, the effect of capacitance C1 and C2 causes output to fall at a rate of 20 dB per decade at increase in frequency. Okay, now how this happens I'll show you in waveform. This is only 120 dB, right? Another 20 dB, how it gets? Further 20 dB per decade fall will be added with another network added due to capacitance C2 and R1. C2 and R1 is this C2 and this R1 will contribute for 20 dB per decade, and C1 and C2, the effect of C1 and C2 will cause another 20 dB per decade fall. Oh, sorry, I made a mistake here. This should be one resistor, right? Which resistor I have chosen? C1 R2. Yes. The effect of C1 and R2 I will mark here. The effect of C1 and R2 will contribute first 20 dB, and R1 and C2 will contribute another 20 dB. Okay. So total becomes, hence the two gain reducing effect combine, gain reducing effect, right? A fall with 20 dB, a fall of gain with a rate of 20 dB is gain reducing effect, isn't it? Your gain starts reducing, falling down. So it is also called as gain reducing effect. So 20 plus 20 will combine together to produce total how much? 40, right? A fall of rate of 40 dB per decade. 40 dB per decade, isn't it? Let us see the design. Design means how will you get the values or with the equations? How will you determine the value of R1, R2, R3, C1 and C2? Now here you remember this formula, R1 equal to 0.1 VBE by IB max. You remember this 0.1 VBE by IB max. This was your R1 in first order, right? Now your in place of R1 there is another resistor, like it is R1 and R2. Another resistor is added. So this R1 plus R2 will be considered as input resistance now together. So it will not be just R1, it becomes R1 plus R2. R1 plus R2 becomes here 0.1 VB by IB max. Okay. Next, what is remaining? R1, R2. Then yeah, R3. What about R3? Here R3 should be equal to R1 plus R2, isn't it? Why is this? So that it should work as a voltage follower. The input side resistance should be equal to feedback resistance, then only it will work as a voltage follower. This is must. Then capacitance. How will you find capacitance? Visible, right? Yes. Capacitor, if it is C1, XC1, XC1 equal to root 2 times of R2 at cutoff frequency. C2 should be taken as twice of C1. Okay. Therefore, R1 equal to root 2 XC2 at FC. Okay. Much detailed derivation for this steps are not needed for you. Okay. If you get this question, you need to draw this circuit diagram neatly, show the frequency response, write the statements neatly. Okay. No need for you to go much deep into the equations like we went into our first order. Okay. You can directly write like this. This much is enough. Okay. Fine. So let us solve one problem on this. Design a second order LPF, means low pass filter. Okay. LPF means low pass filter circuit as shown below to have a cutoff frequency of 1 kilohertz. 1 kilohertz. So first draw the circuit diagram. How it is? This V0. This should be your, what name we have given? This should be R3, right? Here you have one resistor R1, another resistor R2. R1, R2, one capacitor here grounded, another capacitor taken and connected to output side. This was C1, this was C2, right? Remember this, huh? Don't go wrong into this. You can change the names, but their formula will change, huh? If you change the notations. Yeah. What we have, first one to find input side R1, R2, R3, right? We know that R1 plus R2 equal to 0.1 VBE by IB max. This is nothing but, yesterday we have calculated this. 0.1 VB is 0.7. IB max is 500 nano 10 to minus 9 amperes. So this will give you R1 plus R2 equal to 140 kilo ohms, right? 140 kilo ohms. If this total is becoming 140, what is R1? R1 equal to R2 equal to 140 kilo by 2, that is 70 kilo ohms. Both will equally share the total resistance, right? So standard is 68 kilo ohms. Because 70 is not available, 68K is available. Once again, let me remind you that a list of standard values for a capacitance, inductance, resistance will be provided to you, okay, for your reference. Where it is available, let me tell you, in your David Bell textbook, okay, operational amplifier, David Bell textbook, at the last few pages is provided with the standard values for capacitance, inductance and resistance, okay. Now what should be the value for R3? R3, yes, R3 is R1 plus R2, isn't it? That is, how will you do now? Do we have 70 plus 70 is 140, but we have chosen standard as 68. 68, what will you do? 68 double is, yes, 60, 70, 140, 140 minus 4, 136. 136K is a standard already. Is already a standard value of capacitance. So this is your first answer. This is your second answer. What else is remaining? C1 and C2 is remaining. Just concentrate here. We have XC1 equal to root 2 R2 at FC. You need to remember this. XC1 equal to root 2 times of R2 at FC. Okay. This means that you can write your formula like this. That is C1 equal to 1 over 2 pi cutoff frequency of, right? Okay. XC1. What is XC1? This is from basics, huh? This I am writing from this. We know that XC equal to 1 over 2 pi FC. You know this, right? This is from basics. So I have taken here C and 1 over 2 pi f XC, right? Here XC becomes XC1, C becomes C1. Okay, alright. Same thing is written here. So here XC1 is equal to root 2 R2. Root 2 R2. Do we have all of this? FC we have, R2 we have. Yeah, we will get C1 value here. 2 pi, FC is 1 kilohertz. Root 2, what is R2 value? We have decided 68 kilo. 68 kilo. So this should give you 1655 picofarad. 1655 picofarad. Around 1600 may be available as standard, right? So this should be your C1 value. What about C2? We know that C2 is equal to twice of C1. Therefore, C2 is equal to double of 1600 is 3200 picofarad. This is your C2 value. This is your C2 value. All right. Yes, that's it. This will end your second order low pass filter. Okay. Next class we'll have first order high pass filter.